Hi, I'm going to be making my exam for quantitative. So, for part A, it's asking to determine the rate of change in magnetic field, and we're already given the magnetic fields in an initial time and then a final time. So what we basically do is take the change on both of them and divide the change in B over the change in time. And since we're given the formulas, I just plug them in, and so that's how I was able to get my answer. The rate in magnetic field to be 150 teslas per second. And on B, it's asking for to draw the electric field where the legs are at. So these tiny dots are the legs, right? So the magnetic field will orbit around it. It doesn't matter if it goes counterclockwise or clockwise on an MRI machine. So for part C, it's asking to determine the magnitude of the electric field, and so I just used Faraday's law, and so I was able to get rid of the dot product, right? And then I got E out of the integral. So then this is what I ended up with, E times length, which is equals to I also manipulated this equation right here. I got rid of the dot product and then put a B outside of the integrand, and so this is how I was able to make E times length is equals to the change in magnetic field over the change in time times area. Alright, so I just did all my calculations, plugged in numbers, and so I was able to get my electric field to equals negative 22.86 Tesla meters per second. But since it's asking for the magnitude, it doesn't really matter if it's negative, it's just, so that's why I put the absolute value on it. Right, for part D, we need to determine the voltage across the nerve membrane, and for that I use the EMF formula, which is also voltage, which is E times the distance that we're given and the electric field that I just found a while ago on part C, and so I just multiply them together, and so the nerve will not fire since it is significantly smaller than 20 MV. So for part E, the tough one, is the mean one. So what I did, I took Maxwell's equation and Faraday's equation and I set them equals to each other, right? Like right here, right? So, with some manipulation, I was able to get rid of the dot product here, then move the E out of the integrand right here, and so that's how I was able to get the electric field times the surface, which is a cylinder, so it's the circumference of the cylinder, which will be 2 pi r. And so the magnetic flux right here is equals to the magnetic field times the area, but since it's a cylinder, we'll use volume instead of area, and so it would be, then we set them again equals to each other with the plugged in values. So we would have E times the circumference is equals to this formula right here, and so I just divided the 2 pi r to this one right here, and so that's how I was able to get my E alone. So we can find the dt later on. So plugged in my values, right here for distance, radius, and change in magnetic field. And so that's how I was able to get 7.38 times 10 to the negative 8 divided by dt, and that is equals to the voltage. And so for the minimum voltage that we're given is here, right here, so we isolate dt, and so we divide the 7.3 times 10 to the negative 8 by 20 times 10 to the negative 3 to get 3.66 times 10 to the negative 6 seconds, which is the minimum amount of time safe to rise t.